Welcome to my YouTube channel. Today is our lecture number 5 of linear algebra course. Today our topic is about linear combination. So what is a linear combination? If we have vectors in Rn and there are p vectors, that is v1, v2 and vp, and Rn means that each of the vector has n components, and scalars c1, c2 and cp, then the vector y in Rn defined as y equal to c1 v1 plus c2 v2 plus cp vp, that is y is obtained from this combination, that is we multiply v1 with c1, v2 with c2 and vp with cp, and then we add all of them. This arrangement is called a linear combination of these vectors v1, v2 up to vp, and we say that y is obtained as a linear combination of v1, v2 up to vp. These constants c1, c2 up to cp are called the weights. So the weights in a linear combination can be any real numbers including 0. For example, we have this arrangement square root of 3v1 plus v2. Similarly, we can write half v2 as 0v1 plus half v2. So in this case the weights are 0 and half. Similarly, the null vector can be represented as 0v1 plus 0v2. If we move to a geometric description of linear combination, so here in plane we have two vectors v1 and this is my vector v2, and then we multiply this v1 with one scalar c1 and v2 with another scalar. So if I multiply v1 with 2, I will have this as 2v1. Similarly, if I multiply v1 with 3, this vector is 3v1 and so on. Similarly, minus v1 is this vector, minus 2v1 is this vector, minus 3v1 is this vector. Similarly, this is my v2. So this is 2v2, 3v2, 4v2 and so on. Similarly, this is minus 2v2, minus 3v2, minus 4v2 and so on. So now if we form their linear combination, so for a single value of the weight c1, for example, if c1 is 1, I have this vector, and assume we change all the values of c2, that is c2 assume all possible values. So if c2 is 1, I have this vector using the parallelogram law, I have this as a linear combination of v1 and v2. If I take c2 to be 2 and c1 once again 1, so 2v2 plus v1 is this vector starting from origin to this point and so on. Hence, what do we have at the end? That for all values of c1 and c2 shown in this graph, which in this case are integer multiples of v1 and v2, we have all these points covered as a linear combination of v1 and v2. So now we move to the general problem. Assume I have m vectors v1, v2 and vm be vectors in Rn, and consider any b vector in Rn. The question is, can this vector b in Rn be written as a linear combination of v1, v2 up to vm? That is, do there exist weights x1, x2 up to xm such that this vector b can be obtained from the linear combination of these vectors? So we know about the linear combination of these vectors, that the linear combination of these vectors would be x1 v1 plus x2 v2 plus xm vm. So this is the linear combination, and asking the question that whether b can be expressed as a linear combination of this, we have this problem, and which can further be simplified to x1, since these are vectors in Rn, hence each vector has n component, hence this can be expressed as v11, v21, v31, vn1, and similarly the last one would be xm, v1m up to vnm equals b1 up to bn, which can be written as a system of n equations and m unknowns. As for example, this is x1 v1 1 plus x2 v1 2 plus xm v1 m equals b1. This is the first equation. The second equation in the system would be x1 v2 1 plus x2 v2 2 plus xm v2m equals b2, and the last equation would be x1 vn1 plus x2 vn2 plus xm vnm equals bn, and hence this is equivalent to a system of n equations and m unknowns. Now, if this system is consistent, then B can be written as a linear combination of the given vectors v1, v2 up to vm. And if the system is inconsistent, it would mean that B vector cannot be expressed as a linear combination of these m vectors. So for example, I have two vectors in R3, v1 is 1 2 minus 5, v2 is 2 5 6, and B vector is 7 4 and minus 3. The question is, can B be expressed as a linear combination of v1 and v2? So as discussed above, this is equivalent to that if I have scalars x1 and x2 such that x1 v1 plus x2 v2 equals B. Now, if this system is consistent, then we will say that B can be expressed as a linear combination of v1 and v2. And if this is inconsistent, we will say that B cannot be expressed as a linear combination of v1 and v2. Now, this can further be simplified to x1 times 1 2 minus 5 plus x2 times 2 5 6 equals this vector, which can be written as x1 plus 2x2 equals 7. This is the first equation. The second equation would be 2x1 plus 5x2 equals 4, and similarly we have the last equation. And now the augmented matrix for this system is this one. And if we perform some appropriate row operations, we have this matrix reduced, this matrix AB reduced to a reduced echelon form matrix. And since in this form the rank of AB is equal to rank of A, the system is consistent with x1 and x2 both are basic variables. These are pivot positions, and both x1 and x2 are basic variables, and hence the system has a unique solution given by x1 equals 3 and x2 equals 2. Thus, B can be expressed as a linear combination of v1 and v2 with weights 3 and 2 respectively. Now, from this example, what we can see that if we have these vectors 1 2 minus 5, 2 5 and 6, and we are asking the question that whether 7 4 and minus 3 can be written as a linear combination of these two. So, if we are forming the system, then the augmented matrix is that this first vector forms the first column of the augmented matrix, the second one is the second column, and the last vector B is the last column of my augmented matrix. And hence, we can simplify this further. So, as already seen that we can generate infinitely many vectors from the linear combination of some given vectors. For example, we have seen graphically, or from here for different choices of this x1 and x2, we will have different vectors here. And hence, from the linear combination of some given vectors, we can generate so many vectors. Hence, it is more convenient to study the set of vectors generated or written as a linear combination of some given vectors. That is, we try to combine all those vectors generated from the linear combination of some given vectors in a set, and we discuss that set in general. So we have a general definition that let V1, V2 up to Vm be vectors in Rn. The set of all linear combinations of V1 up to Vm is denoted by span of V1 up to Vm and is called a subset of Rn spanned by or generated by these vectors. Thus, the span of V1 up to Vm is the collection of all vectors that can be expressed as a linear combination of these given vectors, with x1 x up to xm are scalars. So asking whether a B vector is in the span of V1 up to Vm amounts to asking whether the system x1 V1 plus x2 V2 plus xm Vm equals B is consistent or not. Sorry, here B is missing, equals B is missing. So, or equivalently, as we discussed previously, that we form the augmented matrix of this system whose first column is this vector V1, second column is vector V2, and the last column is vector Bm, and then we try to see that whether the system represented by this augmented matrix is consistent or not. That's it for today. Thanks.